Alright, hello, this is our second video looking at the limit of a function, and got a couple topics to look at here. We want to look at one-sided limits, which we kind of previewed, and limits at infinity, which we did not preview before. Alright, so looking at one-sided limits first, remembering what we looked at in an earlier video, we said the limit of a function at a point. We said the limit of f of x as x approaches a is L if we can make the values arbitrarily close to L by taking x sufficiently close, but not equal to a on both sides. Again, that both sides was key. And so what we're looking at here with one-sided limits is saying, well, what if we look at this approaching behavior from, well, just one side? It's called a one-sided limit. No surprises there. So a limit of a function as we approach from just the right or just the left of a specified point is called a one-sided limit. We write, it looks like this. The notation you'll see is very, very similar. Note that you've got that superscript there. So what that means is if you're looking at a number line, let's say, and some value a, if you've got the plus there, that means you're a little bit bigger than a. That's the way to think about it. So we're going from this side, we're getting closer and closer, but we're always a little bit bigger than a, getting a little bit closer, a little bit closer, a little bit closer, a little bit closer, and seeing what happens with the function. So we're again looking at limits, but just that one side, from the positive side. So the number line, the way of thinking about it, it'd be from the right of that value. So that notation means it's the limit of f of x as x approaches a from the right. All right, similar situation. I don't know. Let me color it this way. Again, notice, really easy to overlook this, but we want to notice that superscript. And again, we're seeing what happens to the function as we get closer and closer to this input, but now with the minus, we think, well, it's a little bit less than a, so we're out here getting closer, getting closer, getting closer, 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 but only looking at what happens on that side. So that would be a limit as we approach from the left. So one thing we can note, and we'll come back to this later, but if the one-sided limits are the same, the limit exists. We don't usually say two-sided limit, we just say limit. And the reverse is true. If the limit exists, then the one-sided limits are the same. We'll talk more about that later. But if we're looking at an example, this was an earlier example we had. We said, well, as you approach from, as we go from this side, a little bit less than 7, the function value is getting closer and closer to 6. As we go towards 7 from the right side, using bigger values but getting closer to 7, the function value is getting closer and closer to 2. We looked at this at the end of a previous video. All right, so the limit at x equals 7 does not exist. We said that before. However, the one-sided limits do exist. And we mentioned this in a previous video. If you go back and look it up, well, we just didn't use that language. We just kind of wrote it out. Sorry, we didn't use that notation. We just wrote it out. So again, this says the limit as x approaches 7 from the right, or the limit of f of x as x approaches 7 from the right is 2. The limit of f of x as x approaches 7 from the left, from this side, is 6. So we're kind of talking about it here. We just try to make it a little bit clearer. All right, the other thing to talk about in this video, we want to mention infinite limits. And so the idea here is basically we've got kind of infinity in the vertical way, in the vertical sense. And an upcoming topic down the road will look at limits at infinity, and that's kind of a horizontal infinity problem. So what we've got for the example here is a graph of this nice rational function. When it's factored in the denominator, you see that you've got that problem at x equals 2, you get division by 0, so it's not defined there. Everywhere else it's defined, works perfectly fine. If you look, so at x equals 2, first of all, it's not defined. That's our first answer. But let's see if we can say a little bit more. At x equals 2 is not defined, but as we get closer and closer to x equals 2, the function values blow up. They get bigger and bigger and bigger. And you can imagine if you picked something like maybe from the right, how about 2.0001, square that, you got 0.0000001, something like that, which is a huge number. Take 1 divided by that, it's huge. And so mathematically what we say is it does not approach a number as x approaches to, so talking about limit language here, what happens at x equals 2, again, not defined. What happens near, it increases, we say, without bound, which just means it gets bigger and bigger and bigger and bigger and bigger. Whatever number you pick, the biggest number you can think of, I can choose an x value such that this is bigger than it. All right, and it's the same from the left and from the right. So in general, if x increases without bound on both sides of a, we write, using our limit notation, we say the limit of f of x as x approaches a is infinity. And if it decreases without bound, we say we've got negative infinity there. This is an example of what we call an infinite limit. Now, one thing to be careful with is infinity is not a number, so we don't, but even though we don't say that the limit does not exist, we just say that it's infinite. So it's kind of tricky language there. We say it is infinity even though it isn't a number, because it doesn't exist in a sense, but it doesn't exist in a kind of a nice, understandable way, in some sense. So if you've got an infinite limit, we don't say the limit doesn't exist, we say the limit is infinity, or the limit is negative infinity. So a little bit of a subtlety there. Example here, nothing to worry about in terms of actual function formula description. But just looking at this, I see from as we approach 5 from the left, looks like it's growing bigger and bigger and bigger and bigger and bigger forever. Same thing from the right, going bigger and bigger and bigger. So based on this graph, we're going to conclude the limit as x approaches 5 of f of x is infinity. So there's an infinite limit. Likewise, maybe not likewise, but it looks like there's a problem point at 3. So we get closer and closer to 3. It's decreasing without bound, getting more and more negative from the left and from the right. So on both sides, we're decreasing without bound, and so we say the limit as x approaches 3 of g of x, that's what we've called it here, is negative infinity. So we say the limit is negative infinity, even though it doesn't exist as a finite number. We say it is negative infinity. And here's the third case, and this is kind of the bad case. So this is a situation where, and it doesn't have to be infinite on, one side could be infinite and the other side not. But this is a situation where from the left, it increases without bound. From the right, it decreases without bound. So this idea of left and right-sided limits aren't the same. And this would be a case where we would definitively say the limit as x approaches 7, or if you like, the limit of h of x as x approaches 7, whatever language you want to use, definitively does not exist. It is not an infinite limit because it doesn't increase without bound or decrease without bound on both sides. So that's the picture that we have. One last note for graphical interpretation. Infinite limits, or one-side infinite limits of a function, are seen graphically as vertical asymptotes. In this case, we'd have a vertical asymptote at x equals 5, that vertical line. Here we've got a vertical asymptote x equals 3. And here, even though it's not, the limit doesn't exist, it's not an infinite limit, we still have a vertical asymptote x equals 7. So that's a connection to a topic that you had in a pre-calc course, where one of the things you look at when you're trying to analyze graphs and describe graphs of functions is you would look for asymptotes, both vertical and horizontal. And vertical asymptotes are corresponding to infinite limits of a function. And what I said earlier about limits at infinity, we'll visit that down the road, and we'll see that connects with horizontal asymptotes. But this is enough for now. So we looked at one-sided limits, and we looked at infinite limits in this video.